So I'm very pleased to be here to present the very last part of research performed during 2 years, and I would like to thank the BSI's Lisbon team for inviting me to present this research work. So it deals with how to exfiltrate data in a way that you are sure you can never be detected. So I'm sorry, my Linux computer was not working with the video, so there is one demo that I will not be able to do, but if you are interested, I can do the demo on my computer right after the talk. So I propose this agenda. I will first explain the different state-of-the-art and non-technique to exfiltrate data, or to protect data, because both issues are connected. Then I will present how to make a malware very difficult, not to say impossible, to analyze. It is the first initial step in order to deploy the exfiltration techniques. And I will explain how to bypass all data leak prevention techniques. And I will conclude. So nowadays, most attacks are performing data exfiltration. And for example, logbit 3.0, the most known case, quite systematically, they put pressure on the victim by threatening to publish data that they have collected. So it can be just a few credentials, but it can be also a complete database. So depending on the environment, it is more or less difficult. So the most difficult case when you consider air-gap environment, so they are not connected. So some techniques are known, but generally the amount of data that you can exfiltrate is very limited, and you can just enforce a very low data rate. So it is just sufficient to exfiltrate, for example, a few credentials. But whenever you are connected, I mean in a network environment, it's more easy, and whatever may be the protocol considered. So, but you have generally to bypass the different traffic surveillance. And in most industrial cases, it is data leak prevention tools. For example, in Azure, Microsoft Azure environment. But when you succeed, it is possible to exfiltrate a large amount of data, huge databases, at a very high data rate, exfiltration rate. And generally, the target environment have a low or medium awareness about this. And most DLPs are not able to really prevent data exfiltration. But the aim of the talk is to show that even if we would have very efficient DLP, it will be they could be defeated very easily. So from the defender perspective, you can perform two actions. The first one is the most common one. Generally, it is an automated or semi-automated analysis, what we call DLP. But especially in the post-mortem step, you can wish to perform a manual analysis of the documents that are currently exfiltrated. So we have to deal with these two issues, and we will show how to solve them. So from the attacker perspective, once again, he has to consider then two different approaches, or he will launch very common attacks, not specifically targeted attack, because he is supposing that only automated detection will be in place. Or you can consider various targeting attack, typically APT attacks. And in this case, you have to consider that the manual analysis will be possible, and you have to defeat it as well. So in this talk, I will focus on a connected environment, but everything can be applied to air-gap environment. And if you wish to have more information about the air-gap environment, I can give you references. So in fact, there are, as most attacks, you have first to deploy a malware. And then the malware will be able to first scout the environment, make analysis, study the environment in order to adapt to the environment and to prevent its analysis and its detection. And of course, even if the malware is scoped and analyzed, it must not reveal the actual nature of the attack. It must fool the analyst, and it will be part of the problem to solve. So we have twofold issues. We have twofold issues. In fact, the attacker has to consider the different challenge and issues to solve. So you can have semantic detection. Most of the time, it is keywords or even behavior profile. The data can be encrypted, but the encryption is very easy to detect. I will explain why. The attacker can use an encryption key in order to encrypt his data, but you have to manage a secret key, which is not very easy, especially when you have to exfiltrate many documents. You have to face the fact that, for example, you can exfiltrate data only through IPsec channel, and the attacker has not the control of the IPsec channel. So how to exfiltrate data despite the fact that there is such a protection. If you want to exfiltrate many data, techniques like steganography are not possible because the embedding rate, the exfiltration rate is very, very low, less than 3%. And you have also to consider the user's behavior because the amount of data, the frequency of exfiltration can also be a detection criteria. So on the defender side, he has to try to solve all these issues, but with the defender's perspective, of course. So as far as the issue, the fourth issue, I will not have time to present it, but you can refer to my talk at CanSecWest, and we have updated on new IPsec hardware in order to adapt the attack. It still works fully, so we can effectively exfiltrate data in order to, despite the existence of IPsec channel, we are just to monitor the IPsec channel and to make statistical analysis. So it's possible. So you can ask yourself why such a study. Is this not to build attacks, of course, but having the attacker's perspective always enabled to be aware of the risk and to try to find solutions. And there are possible applications that are not related to attacks. I will, of course, for sake of clarity, present unitary brick, but of course you can put all together to have something very sophisticated. So for a reason that you will well understand, the old codes and proof of concept are not public, but technical papers explaining that will be, and the slides will be made public. So what are the different non-techniques as far as information protection is concerned, and of course is related issues, data exfiltration. In fact, I have taken the NATO terminology. You have two ways of protecting information. You have what we call ComSec, communication security. So you just protect the information, but not the fact that you are exchanging sensitive information. So most of the time, it is performed by cryptography, but also you have to, in some industrial case, which are very sensitive, you have also to add physical security, or even to fight against electromagnetic emissions. But if you exchange encrypted data, of course, it's very easy to detect. So the other way is to add TRANSEC, transmission security. You not only protect the information, but also the channel, the communication channel. It means that, in fact, you hide the fact that you are currently exchanging sensitive data. So if you look at the transmission, it is innocent looking. You cannot discriminate between two communications, one being really innocent, the other one transmitting sensitive data. And the most known technique is steganography. So in the technique I'm going to present to you, of course, we intend to combine both views, to protect the information, but also the fact that we are currently exfiltrating data. So if we compare from the technical point of view the difference between cryptography and steganography, between ComSec and TRANSEC, in cryptography, you just transform your plain text into a random text, and to be able to go back to the plain text, you must know a secret key. So you have issues related to security management and so on. And of course, accessing the plain text without the key must be complex and infeasible in a finite time. On the right side, you have steganography. So data are, of course, encrypted. So it is a ComSec part. But your encrypted data will be embedded in a covert image. After the embedding, it is not possible to it is supposed not to be possible to make the difference between the image before insertion and after insertion. And after that, of course, the embedding process is also secret key dependent. Then you send the image and you reverse all the process. And in the history of terrorism, for example, Al-Qaeda used steganography to exchange sensitive data. It was a limited use, but it has proven to be the case. So when we compare these two techniques, what are their relative security? In fact, in both cases, the detection is rather easy. On the left, to detect cryptography, for example, here you have a case of the analysis of a binary, Windows binary file, which is partly encrypted. And we use what we call entropy. Entropy is the amount of uncertainty or randomness, if you prefer, of data. So for all the code which is non-encrypted, the entropy is rather low. And whenever you have a peak, it means that you have crypto. And the entropy, which is denoted by H, in fact, normal data, whatever may be the language, is around 4. If you have packed compressed data, for example, packed binaries, you will reach 6. And encrypted data, you have the maximum per character, 8. So it is very easy to detect that you are currently transferring or exfiltrating encrypted data. As far as steganography is concerned, you have on the left, so in fact this drawing shows 2 points that in fact whenever you go beyond 3% of the exportable bits, for example, the least significant bit in a JPEG image, in fact, beyond 3%, there are efficient techniques we are able to detect, to make the difference, to discriminate between a normal image and a steganography image. And if you consider the number n of the possible usable bits in order to embed data, you can use only square root of n. So it means that exfiltrating a large amount of data is quite impossible with cryptography without being detected. So even for a set of a few credentials, the use of steganography is not recommended because you will be detected. So is there another solution? Yes. So it comes from what we call malicious cryptography and cryptology and mathematics. In fact, it is an emerging field. I work on this field for many years. And it can be defined as the interconnection of all the attack techniques with cryptology and mathematics in order to enrich them each other. So there are a lot of applications. Not all are attacks. You can use it for legitimate protection. So the development of super malware, and you have a lot of mathematical theory that enable to build actual malware that are very difficult to detect, not to say impossible. So, and you can also, to perform cryptanalysis, for example, to steal secret key, you can use malware. So it is a case where malware can be used in order to do what we call applied cryptanalysis. To make recon, for example, thanks to mathematical properties, we were able to design and build code that were able to detect on which kind of processor they were executed, and to decide to activate or not the illegitimate the malware part. In fact, you have to compute mathematical functions, and depending on the result, you will know whether you are on a given class of Intel processor or ARM, and so on. We are able to discriminate very precisely the different kind of processor family. And ultimately, it is possible to use mathematics in order to build block ciphers with trapdoors, encryption ciphers with trapdoors. And in 2019, I was decided to present algorithm with trapdoors. And if you want, you can go to our talks at Black Hat Europe. You have published and published an algorithm which is very similar to the AES, the international standard. And there is a trapdoor, and in less than 30 seconds, you are able to break and find the key. So malicious cryptography and mathematics must be considered in cybersecurity because it is the power of mathematics and cryptology to the service and to the benefit of attackers. So the first part is to use a malware, but malware can be detected, can be analyzed, and the reverse engineer can understand more or less quickly what the malware actually does. So the main tool is what we call non-trivial deniable cryptography. Deniable cryptography is known for a long time, but only a trivial case called one-time pads was known until now. So in fact, it consists to take two random sequences, and adding to the text, and you have two random sequences, each producing a different plain text from the same ciphertext. But of course, if you have a very long ciphertext, it's not practical because you have first to embed the random sequence in the malware code. So the key will be leaked and compromised during the reverse engineering step, and it is not practical. So last year we have found a practical solution which is non-trivial, and in fact we still consider a ciphertext N, a unique algorithm, and two different plain texts P1 and P2. And we implemented a framework which is able to build the algorithm E on the fly. It takes only a few seconds. And we don't need this time very long keys as long as the ciphertext, but very short keys. So from 128 to 256 bits, which is currently the standard for the key size in secret cryptography. So the algorithm E must be deterministic, so it may be a stream cipher or a block cipher. We are currently working on block cipher version. It must be supposed to be public. It means that even if all cryptanalysts of the world try to analyze it, it should not be possible to break the algorithm. And of course, the secret key is far smaller than the size of the ciphertext, which was a very important condition for operational security. So we discard completely one-time bad. And we have the following equation. From the same ciphertext, depending on the key I use, I will obtain two different plain text. So it seems to be theoretical. Let us say how to apply this in our context. And of course, I have chosen two plain text, but we extend to 3, 4, or 5 different plain texts. It can be generalized. So here you have the security analysis. So we suppose that from the ciphertext C, we cannot guess P1 and P2. And even if we have P1, we cannot guess P2 or conversely. It is a security assumption and condition for the security. So of course, I'm going to present the use in the context of malware, but there are a lot of legitimate applications we have developed with a research and development company. So the code protection, not only malware, but also legitimate program, anti-forensic techniques, and we are currently working on multi-communication channel. You have only one encrypted channel, but depending on the key, you can access to one or two channels of communication. So for the demo, I will not be able to do it now, but right after the talk, I can, on my other computer, I can show you. So we have the application on our context. We have a malware, and encrypted malware. And depending on the key that will be used, you will either decrypt as an innocent-looking code, legitimate or lame malware that will fool the analyst, or if the conditions are met, with a different key, he will decrypt on the actual malware which intend to perform the real attack. It means from the same code, with two different short keys, you will obtain two different code. And of course, the aim and the operation condition is to make sure that the analyst, the reverse engineer, will always have access only of this. He will find a key, he will find a code, he will be happy, he will, okay, I have understood the logic of the malware. While in fact, there is another logic. So, of course, the key cannot be inside the code. Otherwise, it will be compromised during the reverse engineering part. So in fact, we suppose the mode operation supposed to have a command and control, and the malware is in communication with the command and control. So we have designed a very secure and complex communication protocol that use fingerprint, time index, time obfuscation, random connection, environmental connection, condition, and so on. And the malware itself never knows when the right conditions are met. But the malware is able to detect whether it is under analysis or not. We have developed with a PhD student a lot of technique, and you have in the fourth reference at the end of the slides. So the malware, the non-encrypted part of the malware analyze its environment, is able to determine whether it is under analysis or not. And it will send this information to the command and control. And depending on the result, it will, of course, decrypt in one code or another code. And of course, the protocol is done in such a way that the probability that the reverse engineer will access only to the wrong solution will tend to 1. So it means that now we are able to deploy a malware that, let's say, would be quite impossible to analyze, not to say impossible. Now, how to exfiltrate data? And of course, the aim for the malware not to be detected is to hide the exfiltration technique we use. The first, very lame, but it is lame, but it is still very efficient for most DLPs. I have tested against the most famous DLPs that you can buy. They were all defeated. We use simple metadata. When you have a digital document, you have the data, what you see, and you have inside the file, you have a lot of internals, what we call metadata. You have, for example, old version, you have date, the ownership, and so on. And most all the present-day digital format have a lot of metadata. So we have observed a large permissiveness with respect to metadata, and it is very easy to exfiltrate data in this way. Regarding metadata of network protocol, you can see the work of the Polish University, Warsaw University. They did a very nice work exploiting network metadata. But it's the same principle. So, I've taken, just an example, I've taken a PDF file. It was a scientific publication. I just opened with a text editor. And I insert a text within the different PDF part, because PDF is a language. It's a script, like a script. Of course, here I have made the text visible for the demonstration, but it is a lame approach. In fact, you will have to hide it with a specific statistical profile. We are going to see it right after. And you save the document. You can open the document, no alert, the document is still working, and you can test it against most DLP. There is no detection at all. Even very famous DLP from very famous software editor. Just do the experiment. It's very surprising. But once again, for me, it's a lame, very lame attack. Of course, if you can say, okay, there is document integrity in place, because, for example, every document cannot modify without triggering an alert. You can build your own document. It's not a problem. So, in fact, the aim is to produce documents that are mimicking normal document in place. And for this, we are going to use entropy and statistical profile. For example, to take a text and to make it look like a PDF. At least from the perspective of a statistical detector. Of course, for your human eye, you will see that it is not a PDF. But once again, most of the DLPs are automated process. So, of course, you are not going to mimic the statistical profile in such a way that it will be possible for the analyst to reverse the process. So, generally, we use key-dependent, secret key-dependent transformation. So, secret key means that you have key management to deal with. And of course, you cannot hide the secret key inside the code. Otherwise, there is a problem. Once again, the key would be compromised. Could be compromised during the reverse engineering part. You cannot, like ransomware usually do, use the crypto API to generate random keys, because the attacker has to retrieve the document and to be able to decrypt it, contrary to ransomware actors. So, what about the key? Generally, our secret key is a random key. We generate a random key which is short enough in order to be recovered by brute force. So we don't care about key management. It is just a random key. We use a dev random tool. And of course, we have to perform a 2 to 40 brute force attack, but it's not a problem because the work is done once and for all, and you get your you get the file you have stolen. And 240 bits is very easy now with the GPU. It's quite easy to do. So you don't have to use key. You don't have to hide key inside the malware code, and you just exfiltrate your data and you perform crypt analysis. Of course, if you want to do something more sophisticated, you will use, for example, an encryption algorithm with a backdoor. You are the only one to know the existence. So there are plenty of different variants for the encryption part. Or transformation part, because here we do not encryption. Once again, we are mimicking statistical profile. So, and I will, of course, it may sound difficult to understand, but I will show you an example. So, just imagine that you want to exfiltrate data which exhibit, for example, a given statistical profile. For example, PDF. PDF, when you do statistics on PDF, you have a lot of characteristics, and any automated program say, okay, it's PDF. And you want, for example, make sure that your PDF will be detected by your DLP at the text file. So it is your target data statistical profile. For this, you have generally to consider an intermediate profile in order to mix with the data profile. And for this, you have a very useful tool, which is a joint distribution or joint entropy profile. It means that you have PDF, you transform it depending on the secret key. At the end, you have the same information, but which looks like a text file. And of course, your DLP say, okay, I block every PDF, but text is okay. And your text will be exfiltrated. So it's a very general approach, which is very powerful. Of course, depending on these two initial and target profile, you will be able to build to exfiltrate as you want. So just a very simple example. Just imagine that you want to exfiltrate. I keep text from text, just to keep things very clear. Just imagine that you want to eavesdrop this text. You want to exfiltrate this. Okay, if you use, for example, as a target distribution, what we call a second order Markov distribution, you will exfiltrate this. Of course, I fully agree. If you read this, you will say there is something strange. But you have to read it. Any automated process will say, okay. If you want to use a more sophisticated distribution, what we call first order Markov word distribution, you will gain this. You will obtain this. And we are very close to something which looks like English. I'm not that good in English, so I could imagine that it is real English, maybe old English, but it's English. It looks like English. Once again, because we suppose that only automated detection is in place. Okay. But here it's very important because we enable to have nearly 30% of embedding rate. Remember, steganography at the best, 3%. Here, 10 times more. And of course, without detection. So, what happens if there is manual expertise, manual analysis of the text? Of course, we will be detected. By principle, everything will be blocked in order to wait for the forensics analysis. So, is it possible to make sure that even a manual analysis will be defeated? It is possible. So with the same principle, we use more sophisticated distribution. And I would like to show you an example of I take on the dark web a critical database. It was a database of sysadmin of that size, 1,494 bytes. And the target distribution was a firewall log. Because generally firewall log exchange are made more or less public. And it was possible to embed this on a file of nearly 9,000 bytes. So with an embedding rate of 70%. So I hope that I will be able to show you the result. So I'm sorry, but okay. I have just anonymized the password. They were in plain, but the number of X is the same as the length of the actual password. So this database, we want to exfiltrate it. Here's the result. It looks like firewall log. And of course, I choose firewall log. Here it is just a file, but I can hide every line in a more huge firewall log file. And I can make sure that even the insertion on the bigger log file will be random and secret key dependent. So it means that you cannot detect this. And you can use as many different target distribution you want. You can adapt to PDF. You can adapt to any language you want. This approach enables to really defeat manual analysis. People will see normal text, and they will consider that this normal text can be exchanged outside. And of course, data will be exfiltrated. So once again, there are a lot of possibilities. You have a quite infinite number of distribution. Initial distribution, target distributions. And you can even use tag techniques. You can, there are quite infinite number of solutions. So from a security point of view, of course, we're asking, I'm currently working on cloud security. Is it possible to prevent this? In fact, DLP are all defeated. And we can prove what we call provable security, or it is provable insecurity, that we cannot detect this. For automated analysis, for some cases, we can recode or transcode the file in order to destroy data would be hidden inside the file. But the last techniques were at the semantic level. It means that even if you recode the text, you will not destroy the information. You would have to rewrite the content of the file, which is, of course, impossible. So it means that, in fact, we have to be very careful about data exfiltration because we must not trust DLP that much. I do not say that you don't have to use DLP because it's like antivirus software. They are useful for many attacks, but for targeting attacks, for very critical environment, DLP is just a false sense of security. Of course, DLP, it is a point that we must also take into account. DLP also use behavioral detection techniques. For example, the frequency. Recently, we have blocked one employee who was trying to download massively sensitive data, and the fact that the download was massive on a limited period of time, of course, triggered an alert. So, may it be frequency, volume, nature of that format of document. In fact, DLP can go beyond the simple static analysis of a document. But the approach is the same. Instead of having statistical and entropy profile for the text, you can design and analyze the same for behavior. And in this respect, it is the same to bypass antivirus. You have static detection, but you have also dynamic detection based on behaviors. So whenever you understand the way a DLP is working, you can evaluate the distribution you're using and mimic it, bypass it. Most of these distributions are often public or known, but a malware can do an intelligent step during the, right after the initial breach, during the lateral movement, and of course can analyze through a preliminary intelligence phase the right target distribution with respect to behaviors. So to conclude, once again, DLP may be useful against basic attacks, but you can honestly try just to use the metadata technique. It's very surprising to see that most DLPs are not using, detecting them. So far more sophisticated techniques will not. So regarding APTs, I think that we have to be aware of that, and I'm even sure that if we have the idea that a few APT already maybe use this kind of trick. So it means that if there is no direct protection, we have maybe to harden the security assessment within, for example, within cloud, the security architecture, the data assessment. I recently observed that, for example, data of different sensibility level are not segregated. To have a tight right management, how many people have access to too many documents because the rights and ownership are not correctly managed. So it can lower the issue of data exfiltration. In any case, it will not prevent it. So that's why I would like to make you aware of the fact that it is a very special case of total security is not possible. So I have finished. If you have questions, once again, I can do the demonstration for the first demo I intended to do. And thank you for your attention.
Thank you so much for the presentation. Anyone wants to ask questions to Éric?
And please don't leave, because the next session, as is in video, will be right away, please.
One question over there? No? Okay, thank you so much.
Thank you.